SwayamPrabha. Digital India. Educated India.
Okay, welcome back. We are discussing the second law of thermodynamics, and in this last few lectures we described Kelvin, Planck and Clausius statement of second law of thermodynamics. In this particular lecture we will be examining the Carnot principles, idealized Carnot heat engine, refrigerator and heat pumps, and in the end we will be developing the absolute temperature scales and finishing up this particular module on the second law of thermodynamics with an example. So let me just go through a bit of what are the different limits which have been put on the operation of a cyclic device. So we have Kelvin, Planck and a Clausius statement, and these statements does put some conditions or limitations on the operation of cyclic device. It states the following: that heat engine cannot operate by exchanging heat with a single reservoir. That's one statement, comes directly from Kelvin, Planck statement. And the refrigerator cannot operate without a net input from an external source. Okay, so based on this statement we can draw conclusions, and this conclusion can be summarized in the following form. So that is something which we are going to state as a Carnot principle. So these conclusions are the following: that efficiency of an irreversible heat engine, which would be the actual heat engine, is always less than the efficiency of a reversible one operating between the same two reservoirs. So that's the first statement, which is the conclusion based on this statement from the Kelvin, Planck and Clausius statements. And the efficiency of all reversible heat engines operating between the same two reservoirs are the same. Okay, and this essentially we are going to state that these are the principles which we are going to call it Carnot principle. Okay, so let us just examine here based on this principle, that you have one high temperature reservoir at a temperature TH and a low temperature reservoir at a temperature TL. What the statement here is, first statement states that the reversible heat engine will always have higher thermal efficiency compared to the irreversible heat engine, which essentially means that efficiency of irreversible heat engine will always be less than that of a reversible heat engine. And if you have two particular heat engines which are operating between the same reservoir, here is another example, heat engine 2 and 3, which are reversible heat engine operating between these two reservoirs having temperature TL and TL, they will have the same efficiency. Okay, so that is what we are going to summarize as a Carnot principle. Okay, so we can prove this principle. We can assume that, let's say, the Carnot principle 1 is violated. So this would be the example. So we're going to try to prove the Carnot principle. So here we're going to assume that irreversible heat engine, okay, heat engine is efficiency of the irreversible heat engine is greater than that of a reversible one. Let's assume that. So what does that mean here is the following, that essentially the work output here, okay, would be more than for corresponding reversible one. Okay, or in other words, that heat rejected here for the case of irreversible heat engine will be less compared to that rejected for the case of reversible heat engine. Okay, now what we can do is we can reverse this second heat engine and make it refrigerator. So now essentially what you have done is you have reversed it, and this is rejecting QH to the reservoir, and here this was the work output for the reversible heat engine. Now you have reversed the cycle, and hence this becomes the input. Okay, now this particular heat which is being extracted here for the irreversible one and now it's rejected to the high temperature reservoir, this can directly be sent here to the irreversible. Thus this will eliminate each other in a sense when you consider as one particular device. So this could be combined in this form. So this cancels out, this particular heat QH could be part of the internal mechanism, and what remains here is the following, that this essentially is work output and this is a work input W reversible. Thus overall work output, considering that the W irreversible is greater than W reversible, is now can be summarized in this form. And similarly for the case of Q to the low temperature reservoir can be now written in this form. Okay, considering that we have reversed the directions here, so it would be QL minus QL reversible. Okay, so now what you have is a device where essentially it's extracting heat from a single reservoir and producing a network, which essentially is violating the second law of thermodynamics. So considering the fact that you have violated the first Carnot principle is equivalent of stating that you have violated the second law of thermodynamics. In a similar way, you can also prove the second Carnot principle. Okay. Let's now look at specifically the thermodynamic temperature scale, okay, which essentially we have discussed much earlier in the initial part of this course, and we have said that thermodynamic temperature scale is nothing but is independent of substance. Okay, what we know is that all reversible heat engine operating between the same two reservoirs have the same efficiency. Okay, so that is the Carnot principle states that. Okay, now since the reservoirs are at constant temperature, the efficiency of reversible heat engine can be written as in this form. So this is a heat engine efficiency, which can be written as a function of these two temperature, considering that the reservoir are at a constant temperature. Okay, and considering the fact that all reversible heat engine operating between two reservoirs, they must have the same efficiency. So this is the Carnot principle which we are making use of it, and we are also making use of the fact that the reservoir operate at a constant temperature. Thus, efficiency of a reversible heat engine should be a function of TH and TL. Okay, now we know that your heat engine efficiency can be written as 1 minus QL by QH. Okay, that is the work out divided by heat in. Okay, for the case of a reversible one, this is essentially G TH TL. So this we can conclude that QL by QH is also a function of TH TL. Okay, now consider this particular illustration here. You have two thermal reservoir, one operating at T1, other was T3, and here we are considering another kind of reservoir which is at T2. Okay, now you have three specific heat engine, and the corresponding work output and heat input and heat extraction and rejections are given. So let's start with the reversible heat engine A, and I'm going to write this as Q1 by Q2 as a ratio of 1 and 2, can be written as now as a function of corresponding temperature T1 and T2. Okay, I can also write Q2 Q3 for the case of the second reversible heat engine as function of T2 T3. Okay, and for the case of third or C reversible heat engine, it can be written as Q1 Q3 F T1 T3. Reversible heat engine C is basically the equivalent of these two intermediate reversible heat engine. Okay, so now we have this information based on the Carnot principle and based on the definition of heat efficiency. You can now write Q1 Q3 as Q1 Q2 Q2 by Q3, and this essentially is F T1 T2 F T3. Okay, now you have left hand side which so function of temperature. Okay, and this right hand side should also be a function of temperature. Okay, and should be independent of T2. Okay, so this is something we can conclude based on this analysis on your efficiency and as well as the definition of the Carnot principle. So let me further get into this what we have written here and define what kind of function we can consider. So this function which we are talking here is a function. There could be many forms. So what we are making use of the fact that this particular expression based on which you can conclude this. So what we can come up with a function f, which is simply the ratio of this function phi, will be the one which would satisfy the previous statement. So here what we have done here is that this function is simply a ratio of phi which depends on only the temperature, and similarly the phi f T2 T3 can be simply the ratio of phi at T2 and phi at T3. Okay, and there's your Q1 by Q3 which is a function of T1 and T3 independent of T2 can be simply written as phi T1 divided by phi T3. So this is one of the functions which satisfy the previous conclusion. Now for a reversible heat engine which operates between TH and TL, you can write QH by QL as simply phi Th by TL. Now there are many functions which would satisfy this. One of the functions which was proposed by Kelvin was simply replacing phi T by simply the temperature in absolute term. So in other words, based on the Kelvin proposal, we can write QH by QL for the reversible heat engine as simply the ratio of Th by TL. This became the basis of your Kelvin or thermodynamic scale, okay, or Kelvin scale. So in the Kelvin scale, the triple point is fixed at 273.16 Kelvin, or the magnitude of the Kelvin is basically 1 by simply 273.16. That becomes the Kelvin unit, okay. So which is nothing but the temperature between the absolute zero and triple point temperature of the water, okay. The temperature in Celsius is simply related to your Kelvin in this form, which we have already discussed. Now this is a very cumbersome way to calculate temperature or to measure the temperature. Better way, of course, is to make use of constant volume gas thermometer. Okay, but what we are going to make use of it is the expression of QH by QL for the reversible heat engine as simply as TH by TL. Okay, and this particular kind of hypothetical heat engine which operates on this reversible Carnot cycle would be called Carnot heat engine. So let me just describe a bit more here. Okay, so for any heat engine, reversible or irreversible, we know that the thermal efficiency is simply 1 minus QL by QH or W net out divided by QH, right? Okay, so now if you are assuming that your heat engine operates on a reversible Carnot cycle, what you can do is you can replace your QL by QH by simply TL by TH. So this is the efficiency of a Carnot engine, okay, and that will be called Carnot efficiency. So this will be the highest efficiency of a heat engine which operates between the two thermal energy reservoir at a temperature TL and TH. Okay, so you can clearly see that if you increase the temperature of the high temperature reservoir, the efficiency will increase, or the way around, if you can decrease the temperature of the load or sink temperature, then the thermal efficiency will increase. Now we can compare the real process with this reversible process. Reversible heat engine is defined as this, as we have already mentioned, okay, so that is your this definition. So irreversible heat engine should be, the efficiency of irreversible heat engine should be low than compared to the reversible one, and this would be impossible heat engine. You cannot have any heat engine which can be greater than the efficiency of the reversible one, okay. So that is a comparison of the Carnot heat engine. Okay, so let's take a simple example of a steam power plant where the TH can be 1000 Kelvin and TL as room temperature 300 Kelvin. So the maximum efficiency based on eta theta reversible 1 minus TL by TH or 1 minus 300 by 1000 is going to be 0.7 or 70%, okay, and actual efficiency will be much lower, 40% approximately, okay. So we, as we already mentioned, the efficiency of heat engine increases with the decrease in TL or increase in TH. So the thermal efficiency of an actual heat engine can be maximized by supplying heat to the engine at a maximum temperature, which will be limited by the metal strength of the heat engine, and rejecting heat from engine at a lowest possible temperature, which will be limited by the cooling medium. Okay, so let me take an example to illustrate the learning of a Carnot heat engine. So this is an example of a Carnot heat engine which receives 650 kilojoule of heat from a source of unknown temperature and rejects 270 kilojoule of it to a sink of 24 degrees Celsius. And we have to determine the temperature of the source and the thermal efficiency of the heat engine. So let's start with the first definition of eta. Okay, so eta thermal reversible 1 minus QL by QH, this will be 1 minus TL by TH, okay. So this is nothing but 1 minus 250 by 650, or this would be 0.615. So that will be your efficiency, okay. This is also equal to TL by TH, which essentially means TL by TH is nothing but 250 by 650, okay. So we already know your sink temperature information, so TL is known. Now this TL has to be in absolute term, so this should be your 24 plus 273.15 Kelvin and TL 25 by 65, okay. So you can calculate your TH as TL into 650 by 250 or in other word this would come out to be Kelvin. Okay, so this is a simple exercise which make use of the definition of thermal efficiency of a Carnot heat engine, okay, where we have replaced 1 minus QL by QH is equal to 1 minus TL by TH. Now let me just describe a bit of this understanding that you can, for the case of a Carnot heat engine, we have written already this, and we've already mentioned that higher the temperature of TL, higher is the efficiency, which essentially means that the conversion is going to be higher of the heat to work. Okay, so energy has a quality and as well as quantity. Okay, and this particular aspect of your eta and the conversion of by QH by TL by TH suggests very clearly that your eta efficiency increases with temperature, which is shown in this form. So in other words, you can have a higher conversion of heat to work at higher temperature. So in some sense the quality of the energy is much higher at higher temperature. Okay, and this is something which is illustrated in this form, that the quality increases as your temperature thermal energy increases. Okay, so let me summarize this aspect, that the work is more variable form of energy. We already have discussed this fact that work can be completely converted to heat but not the reverse, and thus your work is of high quality compared to heat. Okay, so quantity, as we already know, can be conserved, but you cannot conserve the quality. So that means heat cannot be completely converted to work, which means that your quality is not conserved. There is a different quality of work and a heat. So in a sense we can say that 1 unit of high quality energy is more useful than, let's say, 3 units of low quality energy. Okay, or typically when in a heat engine, when we waste energy, this would be equivalent of converting it to less useful or low form of quality of energy. Thus it's important that whenever we look at the process, we should not just talk about the conservation of quantity, we should also look into the quality aspect. Okay, so let me now touch upon Carnot refrigerator and a heat pump, which is based on a similar principle. A refrigerator or heat pump based on a reverse Carnot cycle, particularly we have already discussed the Carnot cycle, now we are talking about the reversed Carnot cycle. So now particularly the refrigerator or heat pump, if they are based on reverse Carnot cycle, they will be called Carnot refrigerator or Carnot heat pump. And we already know the coefficient of performance for Carnot refrigerator and Carnot heat pump. So remember, this is here, this is nothing but your QL, because you are going to extract this much heat in order to keep the temperature of the refrigerator certain temperature, maintain it at a certain temperature. This is nothing but this divided by whatever the work you pumped in. Okay, it is W net in. Okay, which is of course QL by QH. And similarly you can write this, because the desired output would be your QH. Okay, so this is your coefficient of performance for the refrigerator and heat pump. So QL is already known, or defined here is amount of heat absorbed from the low temperature medium. QH is the heat rejected to the high temperature medium. Okay, so in the case of a reverse Carnot cycle, what we are going to do is we are going to just simply replace the QL by QH by the ratio of the temperature. So that is what we have written here, and this is the subscript here. Reversible means we are making use of the fact that this is based on reverse Carnot cycle. Okay, so this is for the case of refrigerator, this is case for the case of heat pump. Okay, so this would be the highest coefficient of performance. Okay, so similar to what we have done for Carnot heat engine, you can also do the exercise for the case of Carnot refrigerator. So this is COPR, which is equal to COPR reversible for refrigerator. For the case of irreversible, so this would be lower. For the case of irreversible refrigerator, this will be greater than the COPR, okay, of the irreversible refrigerator. And this would be the case which for the impossible refrigerator, because you cannot have a coefficient of performance of refrigerator greater than coefficient of performance of refrigerator for the case of reversible refrigerator. So this cannot occur. Okay, so this is something simple understanding, that for the case of reversible or any process which are based on the reversible Carnot cycle would be having highest thermal efficiency for the case of heat engine, or highest coefficient of performance for the case of refrigerator and heat pump. So let me end this particular lecture by taking an example. So this is an example of Carnot refrigeration cycle which is executed in a closed system in the saturated liquid vapor mixture region using 0.8 kg of refrigerant as the working fluid. The maximum temperature and minimum temperature in the cycles are 20 degree and minus 8 degree Celsius respectively. It is known that the refrigeration is saturated liquid at the end of the heat rejection. Okay, so this is the start here. It started from your Carnot, it started from your vapor liquid region. Okay, heat is being pumped in, and this process where it evaporates, and here finally at the end of the cycle you have the working fluid is on the saturation liquid line. Okay, and what is being said that W net here is 15 kilojoules. Okay, determine the fraction of the mass of the refrigerant that evaporized during the heat addition process and the pressure at the end of the heat rejection process, which is essentially this. Okay, so let us consider as ideal Carnot cycle. Okay, so if we consider ideal Carnot cycle, okay, then we can simply write the coefficient of performance for refrigerator as TH by TL minus 1, which if you put the TH is nothing but 20 plus 273.15 divided by your minus 8 plus 273.15 minus 1, and this turns out to be 9.464. Okay, now COPR is also your QL by W in, and W in we know net work. Okay, and this essentially means QL is 9.464 into 15 kilojoules, and this is your 142 kilojoules. Okay, so this is the heat supplied, and the refrigerant has evaporated from 1 to 2 state. So we can find out what is your HFG, heat vaporization, at specific minus 8 degrees Celsius. Okay, so let's look at the table. Table A11 gives you HFG at minus 8 degrees Celsius is 240.59 kilojoules per kg. Okay, so QL is nothing but M, whatever the amount has been evaporated, multiplied by your 240.59 kilojoules per kg, and thus you can find out M evaporation, that the mass of the refrigerant which has been evaporated, and this turns out to be 0.694. Okay, so mass fraction, the amount of mass which has been evaporated divided by the total mass initially present. Okay, that is the mass fraction. The question was fraction of the mass which has been evaporated, so thus your mass fraction is M evaporation divided by M total. Okay, 0.694 divided by 0.8, and this turns out to be 0.868. And what about the pressure here? Now pressure here at the end is P4, which is Psat at 20 degrees Celsius. Okay, which turns out to be 572.1 kilopascal. Okay, so that will be the kind of exercise which we typically have to do, and this will be the end of the lecture. Let me just summarize what we have done in this particular module. So we introduced the second law of thermodynamics. Okay, we talked about thermal energy reservoirs, and essentially we defined the thermal efficiency. We went through the statements of Kelvin, Planck and Clausius statements. Okay, we discussed coefficient performance of refrigerators and heat pumps. We also discussed the perpetual motions which violates the first law and as well as the second law, so of type 1 and type 2. We defined reversible and irreversible process, and finally we introduced the Carnot cycle and as well as reverse Carnot cycle. So in today's part we concluded your Carnot principle and then defined thermodynamic scale, the definition of Kelvin scale, and then illustrated examples and made use of this Carnot heat engine and as well as Carnot refrigerator and heat pumps. So that would be the end of this today's lecture and as well as this particular module. So next time we'll start a new sub chapter, and I will see you in the next lecture.